Welcome to the deep dive. Today we're jumping into a fascinating topic, looking at a great set of sources, mostly core revision materials on the physics of waves.
Right.
And our mission, really, is to get to grips with these invisible movers. How does energy get from one place to another without the actual stuff having to travel?
It's a great question. And it really is the bedrock of, well, how so much of our universe works. You're surrounded by them, light, sound, seismic waves.
Everything.
And the single biggest idea, the one that's a bit counterintuitive, is that waves move energy, but they absolutely do not move matter.
That's the one. That's the real head scratcher.
Yeah.
I mean, light is hitting me from that lamp. I can hear your voice.
Yeah.
But the particles from the lamp aren't flying over here.
Not at all.
And the air from your lungs isn't, sprinting across the room to my ear. It's just the energy.
Exactly. It's all about an oscillation, a vibration. The wave is just a disturbance moving through a medium. And once that disturbance passes, the medium itself, the material, it just settles right back down where it started.
Back to what you'd call its rest position.
Precisely. The particles get involved, they do the work, but they just sort of vibrate on the spot. They don't get to relocate.
And this holds true for all kinds of waves.
All of them. Whether it's a mechanical wave, which needs something to travel through, like air or water, or an electromagnetic wave, which doesn't need a medium at all, that rule is constant. Energy moves, matter stays.
Okay, let's nail this down with some proofs, because it still feels a little bit like magic. The sources have some classic examples.
I think the best one is the Mexican wave at a football stadium.
Oh, perfect. Yeah.
You see this shape, this wave of energy just racing around the stands.
It looks like one continuous flowing thing.
But what is each individual person doing? They just stand up and then they immediately sit back down.
Right, so the people are the particles, the matter. They move up and down, but they don't slide sideways into the next seat.
Their net movement is zero. The energy of that disturbance travels, but the people stay put. It's a perfect visual.
And what about the classic rubber duck in the bathtub?
Another perfect example. As a ripple, a wave, passes under the duck, what does it do?
It just bobs up and down.
It just bobs. It doesn't get carried away to the end of the tub. If the water itself were moving with the wave, the duck would be swept away. But it's not. It proves the water particles are mostly just oscillating in place.
So that idea of displacement, how far a particle moves from its rest position, is always temporary.
It's temporary, and it's also the key to how much energy the wave is carrying. The sources make a really important point here about amplitude.
Amplitude being the maximum displacement, the furthest a particle gets from its resting spot.
Right, and the energy a wave transfers isn't just proportional to the amplitude, it's actually proportional to the amplitude squared.
Whoa, okay, so if I double how far the particles are moving.
You're not doubling the energy, you are quadrupling it.
That's huge.
Think about it. A slightly brighter light has 4 times the energy of a dimmer one if its amplitude is double. Or, more seriously, a seismic wave that shakes the ground twice as far.
It's carrying 4 times the destructive potential.
That's the power of that relationship. And it all stems from that temporary wiggle. So the next logical question is, in which direction are the particles wiggling?
And this is where we split the world of waves into 2 big families.
Transverse and longitudinal.
It all comes down to the angle of that wiggle compared to the direction the wave is actually traveling. Let's start with transverse, the one that gives us that classic up and down wave shape.
In a transverse wave, the vibration of the particles is at a right angle perpendicular to the direction the energy is moving.
So if I shake a rope up and down, that's my particle motion.
Vertical motion.
But the wave itself shoots away from me horizontally. The 2 movements are crossing each other.
And that motion creates those high points we call peaks, and the low points, troughs. There's a great memory aid for this one in the sources, using the letter S.
Ah, yes, the seismic S waves.
They're shake waves or shear waves. They move side to side, which is across the direction of travel. All those in and sounds help you remember.
And the examples are everywhere, right? Water ripples, a guitar string.
And crucially, every single electromagnetic wave, light, radio waves, microwaves, X-rays, they are all transverse.
Okay, so that's one direction. What happens if we flip the angle?
Then you get longitudinal waves. Here, the vibrations are parallel to the direction of the wave's travel. The particles are oscillating back and forth along the same line the energy is moving.
Like pushing a slinky toy? A pulse shoots down the spring.
Exactly. And you don't get peaks and troughs. Instead, you get areas where the particles are bunched up and areas where they're spread out.
High pressure and low pressure.
We call them compressions, where particles are squeezed together, and rarefactions, where they're spread apart.
And the memory aid here is the letter P.
Right. Seismic key waves are pressure or push waves, and the particles move parallel to the wave's direction.
The big example here is sound, isn't it?
Sound and ultrasound, they are purely longitudinal, little pushes being passed through a medium.
So to quickly recap, mechanical waves, which need a medium, can be either transverse, like water ripples, or longitudinal, like sound.
But electromagnetic waves, which don't need a medium,
Are always transverse. That's a key distinction.
it is. Okay, so now we know how they wiggle. We need the language to actually measure those wiggles. This gets us into the properties we use to describe a wave.
Let's do the spatial ones first. We mentioned amplitude, the max displacement, which tells us about energy. What about the length of a wave?
That's the wavelength. We use the Greek letter lambda for it, lambda, and it's just the distance of one full cycle, so from one peak to the very next peak.
Or one compression to the next compression.
Exactly. Then we have the time-based measurements. First up is frequency.
Frequency, which we label with this is like the wave's rhythm, right?
It's precisely the rhythm. It's the number of complete waves that pass by a certain point every single second. We measure it in hertz.
And tied directly to that is the time period.
Symbolized with a capital dollars. If frequency is how many waves per second, the period is how many seconds per wave. It's the time it takes for one full cycle to complete.
Okay, so we have wavelength, frequency, amplitude, period. This is the toolkit.
This is the toolkit, and it all comes together in one beautifully simple equation that defines the wave speed.
The wave speed equation.
You take the temporal measurement, frequency, and the spatial one, wavelength, and you can find the velocity. Wave speed, $1 equals frequency, $5 times wavelength, lambda.
That's the one. It governs all waves. If you know how often they're coming and how long each one is, you know how fast the whole parade is moving.
And the sources give a simple example. A wave with a frequency of 50 hertz and a wavelength of 6 meters.
Just multiply them. 50 times 6 is 300. So the wave speed is 300 meters per second.
And the link between period and frequency is just as simple, isn't it?
It's just an inverse relationship. The period is 1 divided by the frequency. 2 at t equals 1/5 ton. A 5 hertz wave takes 1/5 or 0.2 seconds for each cycle.
These equations are universal, but things get really interesting when you apply them to a specific case, like sound. Yes, because sound is a mechanical, longitudinal wave. It completely relies on particles bumping into each other.
So, the closer the particles are together, the faster those bumps can be passed along.
Which means the speed of sound is incredibly dependent on the density of whatever it's traveling through.
And this is where the numbers get, frankly, a bit wild.
They really do. In air, which is a gas, the particles are really spread out, so sound is pretty slow, about 330 meters per second.
That's our everyday experience. But in a liquid, like water, the particles are much closer.
And the speed just skyrockets. It jumps to about 1,500 meters per second, much, much faster.
But then you get to a dense solid, like steel.
And it's almost unbelievable. The speed can be up to 6,000 meters per second.
That is nearly 20 times faster than in air.
It's an enormous difference. Think about a long railway track. If someone hits it with a hammer 4 miles away,
Okay.
you wouldn't hear the sound through the air for about 18 seconds. But if you put your ear to the steel rail, that sound wave would reach you in just 1 second.
Wow. That's a perfect illustration of how the medium basically controls the wave's speed.
It controls the speed, and by extension, the wavelength, which brings us to probably the most profound point from our sources.
What happens when that sound wave moves from the air into the steel?
Okay, so when any wave crosses a boundary into a new medium, 2 things change, but one critical thing, stays exactly the same.
The speed obviously changes. We just saw that. And if speed changes, the wavelength has to change too to keep the equation balanced.
Correct. Speed and wavelength both change. But the frequency, the number of waves per second, is totally unaffected. It remains constant.
So if my sound is a 500 hertz tone in the air, when it enters that steel rail and speeds up from 330 to 6,000 meters per second.
It is still a 500 hertz tone. Its frequency is locked in.
So its wavelength must have stretched out massively to compensate for that huge increase in speed.
It has to. The wavelength becomes about 18 times longer to keep that $F lambda relationship true, because $5 cannot change.
So let's bring this all together for you, the listener. What does this all mean? We've seen how waves are just movers of energy, not matter.
Using the Mexican wave and the rubber duck to prove it?
We've sorted the wiggles into transverse, like light, and longitudinal, like sound. And we've learned how to measure them, finding out that energy increases with the square of the amplitude.
You now have the fundamental mechanics behind every phone call, every light beam, and every earthquake. But that final idea, the constancy of frequency, I think that's the deepest lesson.
Because frequency is what determines the sound we actually hear, right? The pitch.
Exactly. The frequency is the wave's identity. It's the vibration rate that came from the original source.
So even when the wave crosses into a new material and everything about its journey changes, its speed, its shape, its wavelength,
All of that can change dramatically.
its fundamental identity, the thing that defines it, is that specific note or that specific color of light that stays locked in.
It's the one constant. It suggests that even though the medium tries to dictate the terms of travel, the true identity of that energy is set at its birth. That rate of oscillation travels with it unchanged until the energy is gone. And that, I think, is a pretty profound thought to leave you with.